All right, welcome everyone to our colloquium this week. Thank you for coming. It's my pleasure to introduce Kevin Vixie, my colleague and iSciMath co-founder, today to tell you a little bit about his adventures and his life with, well, you can try and figure some stuff out of there. Okay, you probably know him pretty well, but you probably don't know a few things about him. So I just wanted to mention his academic trajectory, which is very interesting. So he started at Walla Walla College, now Walla Walla University. So he's from this region, and then, well, studied in this region, and then went to the University of Washington. Between that, he was at the University of Nature doing a walkabout. Then he went to Oregon State University, Oregon Graduate Institute, Portland State University, then Los Alamos, where he started a big data team that he will tell you about. And then he came here to Washington State University, where we all met him. And as you probably know, Kevin is really a people person, and his immersion in our physics department was the result of 3 personal interactions, one with Fred Giddis, one with his teenage son, and one with an interaction that our previous dean, Matt Jockers, started, and I'll let him explain that to you. So, thanks.
All right. Well, so today I thought a lot about this, and I decided to do this thing entirely by hand on Notability, using Notability on my iPad, which I got a week before the shutdown, very luckily, and it turned out to be a godsend for teaching classes online. So anyway, as you can see, there's a personal story, technical story, and I'm claiming that everything really happens at the boundary, this fractal boundary between them. So first, you're going to zoom through several things and eventually get to more technical things. But the personal story is my father was a polymath musician who I got my first calculus book from. My mother was a nursing professor that started a nursing school in Africa in 1945, long before I was thought of. Music was a huge thing in my family. Like I said, my dad's a musician. Grew up in Chicago, spending time growing up in Chicago. We had box seats there, shook hands with people like Horwitz and Perlman and Eugene Ormandy. Early on, I had a really intense obsession with chemistry, and a little later added violin to that. We moved to New Mexico, a lot to do with actually, in fact, I had asthma. And then I had New Mexico state of mind. If you lived in New Mexico, you know what that is. If you haven't, it's mysterious, and it's hard to make it not mysterious. The land of enchantment, which is the motto for New Mexico, is understood by everybody who's lived there. I don't know how to add more to that, but then my parents died over 8 years. They got environmentally induced cancer, and that was a very big deal for my brother and I. Went to college at Walla Walla, moved to UW, then Oregon, then in this long walkabout, I'll tell you a little more about, got divorced. Really, I was living on the edges of existence. A big deal here was the severe PTSD that my brother and I had that we eventually dealt with. Came out of that more edge of existence, and started working on a PhD in applied physics at OGI. Couldn't get along with advisors, so I finished with a master's. Then I ran a circulation physiology lab at OHSU. I met Beata, got married. Levi was born. Within a few months, I went back to graduate school, which made it interesting. My brother got me going to Al-Anon, which was a big deal for me. Then I ended up at PSU because Andrew Fraser had been very kind to me previously. I decided to do a PhD with him. He had friends at Los Alamos, and I ended up at Los Alamos that way. Anyway, technically, started out in chemistry. I don't know, 8 years old, fascinated with bombs and explosions and stuff. That got me into mathematics because I was reading a physical chemistry book on my own that had derivatives in it. I didn't know what the heck they were. My dad, who was this polymath musician, had a calculus book. He gave it to me, started studying it. I got a degree in mathematics, dropped out of school at UW, and then I did a bunch of stuff. I did engineering consulting. Those who know me know that I'm kind of bold, so I would just try stuff, and usually it works. So I did that for a while, a little bit. I did ocean circulation research at OHS at Oregon State, started this degree in applied physics. the guy thought he'd inspire me to work harder by telling me that when he was doing his PhD, he only saw his wife and kid an hour a week. That didn't inspire me, and I didn't like him. But anyway, I had a friend who was good enough to say, why don't you just finish the project and get a master's, which I did. So then at that time, a little bit after that, I was doing some neurophysiology consulting. I built a heater and a thermometer. Well, I guided the whole construction of this thing. You could measure and you could excite a nerve thermally and measure a nerve cell and measure it so you could like feed in waveforms of temperature and you could verify you'd done it with those tiny little thermometers. So I did that. And then the guy that moved there, neurosurgeon moved there, decided he wanted to hire me to run his microcirculation research lab in neurosurgery. Then I found myself doing mathematics sort of when I was running experiments in this lab. And I decided I'm going to go back and do mathematics. And Andy Fraser was at Portland State. So I started working with him. He's in the system science program. Started doing dynamical systems research. We kind of morphed over to signal processing, inverse problems, data modeling, image analysis, learning from data, and geometric measure theory. That's sort of the string along which it went. Now, I thought about very often when you give a talk, you have acknowledgements at the beginning or the end. And to be honest, they're kind of, you have them there because you have to, or you value the people, but it's kind of, it doesn't feel like it's ever central. For me, people are central. Like without people, I think I'd be dead right now. Both my brother, like I said, my brother and I had really severe PTSD. The kind of PTSD that makes you do things like climb cliffs without ropes, drive your car as fast as it will go, paddle class 5 rivers regularly, that kind of craziness, right? So people for us were huge. So this is a technical and personal chronology. So when I was in second grade, Herbert Federer published geometric measure theory in 1969. He started working on it in 1960. That's the yellow at the top. It's famous for being kind of impenetrable. It's the area that I eventually moved into. 71, a couple of years later, Vatnik and Chervonenkis published their famous paper, which invented the Vixie dimension and made a lot of interesting things in machine learning possible, statistical learning theory. It's influential. It's been cited like over 5,000 times. And in 1974, the year I moved to New Mexico with my family, Almgren started his big paper. This is a geometric measure theory paper. So from 76 to 1980, I was studying music at NMSU and studying books at home. My homeschool was read books I like to read, except I didn't like English books. My mother sat down with me and read through the book, and I liked that because I like doing stuff for my mom. But most everything else, chemistry, physics, mathematics of all sorts, whatever, I read on my own, and I just obsessed on those things. And I obsessed with violin performance. Well, in 1980, I moved to Walla College, and in 84, I graduated the same year that Fred finished his paper. It was a big paper. It's a record-breaking paper, 1,728 pages to be precise. And a couple years later, Andrew Fraser and Perry Swinney published, I think the title is Independent Coordinates for Mutual Information, another paper that became famous. It's over, again, it's cited almost 6,000 times. Andy was going to be the guy I was going to work with eventually. That same year, 86 and 87, I was working at UW, working with Chris Brotherton in atmospheric sciences. He was in applied math, that's where I was. But I was really obsessing with dynamical systems. So he and I did a bunch of stuff. And looking back, I did really well with him because I was extremely keyed into, if somebody loved me, cared about me, it was kind of like, by that time my parents were dead, they cared about me, I would jump over the moon for them. So in his classes, I would be way the top student, way above, right? In somebody else's classes, I would just not go. But I didn't really understand those things because I did not understand the effects of things like PTSD. But looking back, that's the only regret I have from UW, that I didn't finish with him. But anyway, a year later, 1888, Frank Morgan started published his first edition of geometric measure theory, which is this blue book towards the bottom. That became important, and I'll tell you how. In 92, three guys, Rudin, Ocean, and Fatimi, published a paper where they looked at using total variation regularization for image analysis. That is another important part of the story. It's clearly sort of important. It's like almost 19,000 citations for that paper. Then in 93, well, actually late 92, I met Beata, and early 93, we got married. That was a big deal for me and for Levi, who was born a couple years later. And then I began working with Andy. And these names on the side, so notice I have Gabi and McCarthy. Mariana Gabi was the music professor and violinist at NMSU. McCarthy was a retired mathematician, well, sort of retired mathematician at Demi, that spent a lot of time mentoring me. Thompson and Wiggins were the two professors at Walla Walla that kept me in one piece, literally, often. Chris Featherton, I mentioned him, Frank Morgan, Andrew Fraser. So in 96, two things happened in 96. So Devroy, Diorfi, and Lugosi published probabilistic theory of pattern recognition, which is like the standard Bible in statistical learning theory, which is really the heart and soul of AI machine learning. That's where the real things happen. And then David Caraballo graduated under Almgren at Princeton. In 98, we moved to Los Alamos. Then in 99, a bunch of things happened. Evans and Garapi published their book, which is the blue book, second from the top, in which some of you are reading right now because you're taking my measure theory class. It's really quite a remarkable book. I published a paper with Andy, Richard Smith, Eric Smythe on having to do with hidden Markov models and circulation. Important point there is Richard Smith. I'll come back to that in a second. Then I go to the meeting in San Antonio and meet David Caraballo, and he's the Pied Piper of geometric measure theory. To the point that when I get back to the lab, I close my door for 8 or 10 days and go all the way, most of the way through Evans Garapi's book, very obsessively. And that was it. I was, from that point on, I was really into the geometric measure theory. I also published a paper, detection of alias. I put it on the archive. Is the correct word, correct description, and where I solved the problem. So Murray Walensky and David Szigeti had been at UT Austin with my advisor, Andy Fraser, and they were at the lab, and they had an LBRD, which is like the internal NSF at Los Alamos, and they wanted somebody to do it. They didn't have time to do it, so they brought me there, and that's how I got to the lab. So Murray was claiming you could detect aliasing, and people who were establishing signal processing kind of made fun of the idea, but it was actually correct because they weren't reading what he did carefully enough. So I came along and gave an example that showed exactly why what he was doing worked. And that was because if you have a stationary signal, then you have something that I defined called sampling stationarity. And if you sampled the not, you didn't do the sampling correctly, so you weren't sampling at least twice the highest frequency, then you aliased. And in fact, the thing you reconstruct would lose that sampling stationarity. So you could use that to detect aliasing. And this picture has something to do with that. I can show you the details later. So that all happened in 1999. Now, why is that important? Well, because that gave me freedom to do a bunch of other stuff. In 2000, Felix Browder had a meeting at UCLA where he was trying to reproduce, some of you have heard of the Hilbert problems. I think he was trying to do that because he invited 15 people with Fields medals and everybody else is in the National Academy, and they gave all these famous these really good talks. That's where I met Tony Chan and Gene Taylor, who would have a big influence in the future. But at about the same time, Tamasaki and I were doing this work where we said, hey, if you want to do tomographic reconstructions better, you should use the SBD. This is this thing about, I think, that a lot is underappreciated, the idea of arbitrage in science. Where you have an idea that's old hat to you, and these guys don't know anything about it, and you bring it over here, they go, wow, and it solves a problem for them. And that was an example of this case. So about the same time, I started the DD-May team, which is the first big data team at Los Alamos with Tamasaki. Again, these people on the side, Cagliostro, Swart, and Hyman were people in the management or the leadership at Los Alamos that if without them, I wouldn't have done what I did because they supported me. In 2002, I decided I would have an image analysis workshop at Los Alamos, and the power of being at Los Alamos, if you had a good idea, you go somewhere and get money, and very quickly. So I went and had a conversation with this division leader at X division, which I was in at the time. Said, I want to have this image analysis meeting. It's important. Should give me money. And he's, yeah, 50,000, no problem. So he gave me 50,000. And a little bit later, I decided, I need another 30. So I went back another 10-second, well, probably 2-minute conversation. You got another 30. So I got 80,000. And it turned out, for whatever reason, all the people I invited except one showed up. So I had all the big figures in the area. The guy that didn't show up was David Mumford, but he sent his best student. David Mumford had a Fields Medal for algebraic geometry. So in 2005, a paper by Chen and Ezadolu on L1 TV, which you will see, all these stuff will become a little clearer why they're important. In the end, that was published then. And I chaired the summer school at IPAM on images and signals. Another guy in the committee is Jan LeCun. Some of you know who he is. He's a co-inventor of deep learning. So in 2006, I'm at a workshop at IMA at Minnesota, and David Mumford suggests the flat norm. And so this guy who became my postdoc and I wrote a paper that said, hey, actually, this thing we know how to do in image analysis is computing the flat norm, because nobody knew how to compute the flat norm. And that opened a bunch of work. So in 2008, I was recruited here. And then I have those dots, a bunch of students and papers and so on. But the next thing I want to mention is 2018, when Matt Jockers created the committee for the iSchool. And Michael was on it. And I could see that maybe the iSchool wasn't going to go ahead because of cracks I could see emerging, but I knew I could work with Michael. That was a guy I could work with. So we started working. And that same year and the next year, I was on a leave of absence to start. I started a lab, kind of like a really small Google Labs, for a very lucrative, very profitable financial technology company. The thing about that was it was very encouraging, because after being here for 10 years, it was, but 9 out of every 10 ideas people thought weren't that good of an idea. And the 10th one, there was no money for. It's like basically every idea I had, because I thought carefully about them, they liked, and there was always money. It was like a blank check. That was a hugely encouraging experience. Came back and started with Michael and with Bala, actually started the iSciLabs. Now here's a little more, get a little more technical now. So what was it doing at UW? It was dynamical systems. And I think because I'm very geometric, and so some of you have studied dynamical systems, you'll know why I liked it, because it's highly geometric. But because of the PTSD, I didn't know it. I didn't understand it at the time. I just dropped out. I mean, I probably would have finished my PhD in a year with Chris. I was working very, very efficiently with this. But I just quit. I moved to Oregon with this little cult-like group. Oregon has every kind of thing you can imagine. All kinds of groups of people doing all sorts of strange things. And had cousins who were involved, and I went there, rented a little cabin in the woods for $50 a month. Then when I decided I needed money, I did a variety of things. Construction, roofing, worked at a seed farm. I taught grade school. I did get a job at OSU doing ocean circulation research. Then I got microcirculation research at OHSU, and I'm sort of coming back to normal life during this. But I'm doing a microcirculation research, and I'm realizing for entertainment, for education, whatever, I'm doing mathematics all the time. So I decided, this Andy Fraser guy had been very kind to me in the past. I'm going to go see if I can work with him. So I did. And so he kind of worked on the mix of dynamical systems and information theory. That paper that he was famous for was using mutual information to suggest the right time delay for time delay embeddings that were a big thing in physics at the time. Which of course got me into signal processing. And that took me to the lab where I did the detection of aliasing. And that gave me freedom. So this is another place where the emotional history comes into play. That emotional history made me very distrustful of authority. Very, very, very distrustful of authority. And I didn't want anybody to be controlling me at all, which meant I needed to raise my own money. And so that's what I started doing. But the fact that I did this work that they liked gave me freedom to look around. And so I did that. And I found that people were doing these interesting things with tomographic reconstructions. So the thing on the picture on the bottom, on the very right, is a picture of two cylinders of high explosives that are glued together that they detonate. And then the shockwave passes through the interface, and what they're interested in was what the shockwave was doing as it was propagating through the burn products. So they would do, it's symmetric, so they would do like one, if it was perfectly symmetric, all you need is one projection, because all projections would be equivalent. So they use the Abel inversion to get what the actual thing was. But if you actually do that, you end up with, just without thinking about the noise, you end up with very crazy noisy reconstruction. And we said, well, we can use this total variation, that's the Rudin-Osher-Fatimi paper thing, to do a better reconstruction. And we can get this nice clean picture. So we started doing things like that. The thing on the right says SPD underneath of it. That's another tomographic object they created for calibrating methods. And that was a better reconstruction than they could get using simple SVD regularization. The thing in the middle is from an experiment where they were studying Richtmar-Meshkov instabilities. And that's where you have a shock wave hitting. It's hitting parallel and it generates vortices. And we help them using ideas from geometric measure theory. The very thing on the very left, this classification mod invariance, well, in 11 came along and they decided, well, we're going to do something to help with security. So they had an LDRD call, and the guy who's in charge of the spook division didn't like me very much. But luckily, Bill Press sort of liked me. So Bill Press was at the time the chief scientist at the lab. And he said, no, I think Kevin and his guys will do something good. So I'm going to give him the money anyway. So we got the money to do it. And Andy Fraser, my advisor, two other guys and I, created a method for classifying faces that worked better than what was out there at the time. All those things sort of were helping make this team a successful team and us able to get money to solve things. That gave us more freedom. So I spent time at places like IPEM and IMA, where this guy Mumford suggested the flat norm. Now, so it says f of u equals integral, that's supposed to be absolute value of gradient of u. Actually, that's important. The norm, the length of the norm of gradient of u plus lambda times u minus f. So what is that? That's the L1 TV functional that can be used to find a non-noisy image from a noisy image, right? So that the f there is the noisy image, measured image. The u is your candidate nicer thing. And if you just look at that, that's supposed to be the norm of u. So you want integral of the norm of u to be small. That means it's smooth. You want the integral of the absolute value of u minus f to be small. That's close to the data. So you have in lambda controls the balance, right? Bigger lambda, more I care about the data. The smaller lambda, less I care, more I care about smoothness. And it turns out that that's pretty innocuous looking, but turns out the mathematics there is very deep. So because it invokes the first term, which I've written down incorrectly, which is actually, this is on this guy, so I can actually fix it at this moment. There we go. So that first term, correlation term, is really, it opens up very beautiful mathematics. Because, so just think about the fact if u was if it's a cartoon, so it's 0 or 1 everywhere. Then where it's 0 and where it's 1, you'll have derivatives being 0. And where it's a discontinuity, well, it's not defined. Well, it turns out though, it's easy to make sense of it in terms of measures. So the gradient, the norm of the gradient becomes a measure on those boundaries. So you have this generalized derivative that you can use very effectively. And it turns out that that thing, when you minimize it over u, is a particular case of the thing called the flat norm in geometric measure theory you use to measure distances between these generalized surfaces. So the surfaces I'm talking about aren't these just these nice smooth things. Those are examples, but you can get really crazy things that have all sorts of wildness to them, and this still works. And the point of that in geometric media theory is that, so in mathematics, this is how it often goes. I have a problem I want to solve, I have a class of things I want to look in for a solution, and my inclination is usually to start with a class of things I like, this nice. The problem is that you're not guaranteed you have a solution there. So you generalize and say, okay, I'll let wild things, let it be wild, right? And so you find, oh yeah, there's a solution there, but now the problem is, yeah, it could be one of these super wild things. So then you have to involve yourself in regularity theory, which means now that I have a solution, I want to show actually, even though it could be wild, it's actually really nice. Now, most of you have seen this because you've seen Laplace's equation and you've seen the heat equation. You know that if you have a region, a boundary with a wild function, like even discontinuous temperature on the boundary, inside the boundary, the solution is smooth. In fact, it's C infinity, right? So even though you have wild inputs, you can have nice solutions. And so that's an example of something where you get nicer solutions than you assume. Because to write down the heat equation weakly, you need at least one derivative. Just the usual way, you need two derivatives, but it turns out you get infinite number of derivatives. Well, that's the mission that happens here. You write these tools that work for wild things, and then the thing that's challenging is showing it's nice. So in fact, that paper I mentioned earlier, remember the paper was 1,720 pages long? It was a paper that talked about what solutions to the minimal surface problem were like. And it was for higher codimensions. So if I have, something that, if I have a surface in 3 dimensions that's 2-dimensional, then the theory is relatively simple. Papers are only 100 pages long. If I have something where the codimension is higher, that is, it's the difference in dimension between here, it's 1, right? I have a 2-dimensional thing in 3 dimensions. If it's a 5-dimensional thing in 8 dimensions, it's higher codimension. Turns out that the mathematics is much more complicated, and that's what he was solving in that paper. But anyway, I should have mentioned the thing right underneath, the thing the arrow goes to, script F, that's the flat norm. And it turns out those two things are equivalent. And we realized that, and so that led to a sequence of papers with Bala and students, simplicial deformation theorem, median shapes, which is this from that paper. Hopefully that's tantalizing enough, you might go read that paper. We were proving that things that look like the script B in the left were actually solutions, give you solutions to this problem. And the argument was fun. So it involved a new graph theory result, which is this thing at the bottom, because we slice the thing up there, you get those things, you get graphs, and then you want to have, it was a particular property of those we wanted to get. And Matt Huddleston, who's a graph theory guy in mathematics, helped. That actually even led to the approximate traveling salesman problem, which you can listen to today, because Enrique Alvarado, the student that did that with me, or I did that with him and Bala, is giving a talk today and tomorrow, today at 4, tomorrow at noon, about some of those things. Well, all this led eventually, and again, probably because I am now, because by now, like at this moment, I've done lots of counseling, EMDR, all sorts of things, because when PTSD actually moves into your life, it disrupts stuff. And you find that if it's not disrupting things, you're bending yourself out of shape in a way that doesn't lead to thriving, right? So back up a little bit, when my son was, when we're going to an appointment before he was born, my brother calls me up and says, they think they've hit all my guns, but I'm still gonna kill myself. So he was in the process of being sent to treatment from California, which had a very good diversion program. He was a dentist and high access to drugs and alcohol. So anyway, he did go to treatment, he got better, and now he's a big deal in recovery, as well as has a very good dentistry practice. But that was for me the beginning of like going to Al-Anon, facing up the fact that for us, when we watched our parents die over 8 years without emotional support, you ended up starting behaving patterns that worked at that moment. They help you survive at that moment, but that's not a good pattern long term, right? And the thing for me is that, and I'll get to this a little bit later, that had large impacts in my science and mathematics. So anyway, now we're at the TS labs. That's where I'm 18, 19. I'm building that thing out of a blank check, and that's a hugely inspiring and encouraging experience after being here for 10 years fighting. The honest truth is, after a few years, I actually had a breakdown here because I was trying to make things happen that didn't happen. And now I'm going to explain the 3 people that he mentioned at the beginning. So one thing I would do to make myself feel better during those years, I would come over and talk to Fred, because I always feel better to talk to Fred. By the way, Fred worked with another Fred, who was a student with me at Walla Walla way back, Fred McIntosh, right? So I talked to Fred, and my son, who is brilliant in many ways, and one of the ways he's brilliant is with people. He can see in people in ways that are just phenomenal. At one point he said, "Dad, why don't you just build bridges with physics? Like it over there, just go with this." He's a teenager at the time. And then of course Matt Jockers comes along, starts a committee. I meet Michael, and that's the last straw. I just come over here. So that's the explanation of the 3 people at the beginning. So I get back from that leave of absence, start working with Michael, and we start the CDLG and the iSciMath. And at the time, Bala was more involved. We're trying to get him back involved again. And I'm also now really realizing that what really inspires me is working with people, teaching people, explaining things to people, not, writing a 1,700-page paper. There's so much things out there that already developed that are useful that people aren't using, that I want to devote my time to getting people, physicists learning measure theory, and engineers learning actual statistical learning theory rather than just the black boxes. Everybody learning differential geometry or geometric measure theory, because everybody should know it. So what I have up here are 3 examples that you can't read. The one on the left is the maximum distance problem that Enrique is going to talk about. It's more technical, but it's still cool. It's very geometric. Anything geometric is cool. The middle one is something that's really not new ideas. It's just explanations for people that don't know. Cubicle covers. I did this with a student. That was the first paper he did with me. And it was aimed at undergraduates and graduates. It wasn't, I don't know if there's anything really truly new in it. Very little truly new. The thing on the right is a book I've written and I'm editing, and I use for 401 and 402. But to be fair, it's kind of a rough go if an undergraduate thought they had to know everything in it. Yeah. But I think it's pretty inspiring for people to take it seriously. So that's kind of where I'm at now. I want to do technical things that are technical, but I want to do with people. Expository things are huge. Getting people involved, so writing expository things and getting people to understand that are things outside of their usual silos is a big deal. So here's the iSciMath vision. So what's its inspiration? Well, Los Alamos T Division, UBC Science 1, Michael was in the TS labs that I started, blank check, DDMA team, that's the big data team I started at Los Alamos, DDB, where he was at, Center for Theoretical Physics at MIT, and then fairly intimate knowledge of what Bell Labs and Xerox PARC were like. And then there's 2 books, which are shown up there, Range and Culture Code, and if you haven't read them, you should read them. I recommend them to everybody. In fact, the bottom one, I bought 40 copies of and gave away, including one to the president, that when he came and talked to us here, many months ago, he kind of sheepishly admitted he hadn't read, which took his, what can I say? I mean, you can only give things to people, you can't make them do it. Anyway, so what is it? Well, it's a reimagined, updated Bell Labs Xerox PARC-like thing that's in university and has extensions outside of university. So it's a silo-free, intellectual free trade zone. And the idea is that the fluid social environment, which is also collision rich, is just crucial for getting people to move outside their usual little groups. We have jam sessions, have a sprint culture. What is a sprint culture? That's a business idea where you try things quickly. You want to fail quickly so that you know where to go next, right? You don't want to work on something and realize, oh, after 3 years, that didn't work. I missed a sign change back there 2 years ago. And then this maker, sort of a maker state of mind. So what we have is we're trying to develop a rich ecosystem of those multi-threaded classes. And that we're serious actually about that little funky phrase, jacks of all trades and masters of one or two. We really want that. It's not just you want a jack of all trades or you want an expert. You want people who kind of have both, right? And Michael and I maybe argue a little about where's the balance. I think everybody should have jack of all trades, and he thinks that maybe more people should just be, maybe a few more people than I think should be these narrow experts. I'm not sure. But the culture, and the big point of this is that the culture is everything. If you get the culture right, everything else solves itself. If you have the culture wrong, you're constantly fixing it all the time. And you're just so distracted by the things breaking that you don't get anything nearly as cool done as you would get done. So the three things are safety and belonging, basic human needs. And vulnerability, power, connection, because connection is where the interfaces happen. And if you're not vulnerable, then you're not honest. You don't get the high rates of communication going on you need. And then a purpose and vision that are always in front of you. The inspiration that authentically, right? Not just this, oh, we have a motto we put up. That's bullshit. So I don't know how many of you were here, at least the faculty probably were, but I know that I was really irritated when I got here and they had a motto that after a while they took off of the little logo thing. But before they took it off, I edited the logo and took it off because I thought it was ridiculous. It said world class face to face. Like, what the hell? If you're world class, you don't say you're world class. I mean, if you're not world class, if you're world class, you don't say you're world class. If you're saying you're world class, it's just one of those things. But I hate mottos. I'm not talking about that when I say purpose and vision. I mean the authentic thing driving you. You keep that in front of you all the time. It helps you weed out distractions you could get into. That's really important. So if you read the Culture Code, you'll understand. He's brilliant. His collection of anecdotes, stories are brilliant. And I recommend that book very, very highly. So the other thing that, it's not shown there very well, is it? That's it cut off. Anyway, this honest outreach idea is we want to teach a very wide range of people, and there's many reasons for doing this. One is those are the people who actually fund what we're doing, right? Tax dollars of one kind or another is funding this. We should be teaching them what we do. It also makes you able to communicate what you're doing to anybody. So if you want to go get money from somewhere, you're better able to do that, right? It also makes it so that you'll understand what you're doing better, right? If you can explain what you're doing to somebody who doesn't have the background, you have worked on it hard enough to get the simple essence. And as far as I'm concerned, I can only really use something when it's become simple. It can seem complex to other people, but when I've made it simple to myself, now I can go use it to do something. And if it's really at the edge of my abilities, it's hard for me to take that and leap with it. I have to have made it simple to leap. So teaching others actually helps you with all of those things. Here are the classes we've had so far. So geometric analysis with view to use, quantum computation, learning from images and signals, standard model, which is happening right now, measure theory, which is happening right now. And in the spring, the analysis of and on rough sets. So the idea is it'll be computational and applied and pure fractals and that kind of thing. Computation of fractals. Near future with visual differential geometry, topology and geometry, back of the envelope computations. This is this book by, I can't remember his name. It's this light blue thing here. I think it's an MIT book, right? Anyway, and then geometric measure theory with a view to data. So that's geometric measure theory, but pointed at people who want to use it. And the last thing is something I'm arguing with Michael about why it's important. And I think we should teach statistical learning theory so that people really understand what's actually at the heart of learning from data. So other things we have, podcasts, videos, outreach, jam sessions, consulting. These are pictures from various of those things. This iSciLabs is an experiment we did for a summer or two. We did some consulting. It was a lot of fun. We made some cool videos. So here's my why the culture matters. Well, this is my philosophy now. So I think the first do no harm creative innovation requires, if you're really going to do creative innovation where it's first do no harm, it requires an emotionally healthy foundation. Siloed, disintegrated human beings drive innovation, and they, at the same time, they blindly externalize all the negative stuff. And so that creates damage both on a local personal scale and a global scale. And the ingredients, like I mentioned before, the safety, belonging, the vulnerability, power, connection, and purpose and vision. So the idea is that complex system wisdom, the idea that you have to think about all the pieces, the wisdom that comes from that leads to getting the culture right. And siloed expertise, which leads to cleverness, which is very different than wisdom, encourages a cultural tone deafness and a willingness to just externalize all the negatives. And I think it's pretty obvious, you look at the world right now, that there's been vast amounts of externalization that have been destroying everything. So on the personal scale, as I mentioned before, the PTSD, Al-Anon, and the walkabouts that were really spent a lot of time in nature and EMDR have all worked together to help me understand what it means to be emotionally healthy. So I wouldn't be doing this project without that. That opening has made me able to see things that I think are crucial to make this work. And so the values that I've come out of that experience with the complex system wisdom, having authenticity and human connections, honesty, but founded on kindness, emotional health first. Really, you can't get around that if you want something deeply successful. And then organically diverse, collision-rich culture, right? So for me, that results in a qualitatively different technical mode. That's still deep, that's still cool, still do a bunch of stuff, but it's very different than before when I was blind to all this stuff. And you know, part of that's being aware of the team dynamics and the human thriving, just the complex systems view of things. But I had shattered sets in the title. What the heck are shattered sets? So here's what they are. So imagine you have a classification problem. I have a two-dimensional bunch of points, and I want a classifier that, so these are my label. I have all the O's and all the X's. And of course, if I use that classifier I've shown, it perfectly classifies my training data. Question is, how will it do classifying new data? Right? So at the bottom, well, here it says you need a set of classifiers rich enough to classify, simple enough to learn. And you want useful learning bounds. It basically says if I have this much training data, I will have a low probability of classifying new data points wrong. That's the goal, right? So a family of classifiers. So what are classifiers? Here it's just sets. So I have a whole family of sets, and I'm going to, on my training data, I'm going to choose a set. And then for future unknown data, I'm going to, if it's in the set, I'm going to call it a no. If it's out of the set, I'm going to call it X. Now, how often is that going to make me make a mistake, right? So a family of classifiers shatter a set, Z1 through Zn, if they correctly represent any classification on those. So here's what you imagine. You have Z1 through Zn, and now you think of all 2 to n possible assignments of zeros and ones or O's and X's to that, right? If my classifier family is rich enough that no matter what classification of zeros and ones I have, I can correctly classify the training data, then my classifier set shatters that set of points, okay? So that's what it means to shatter, a classifier set to shatter. So here's an example. I have 3 points, Z1, Z2, Z3. If I take all half planes, the family of half planes shatters this set. Why? Because I could class, if I put any assignment of 0, 1, 0, 1, 0, 1 there, I can choose a plane that correctly classifies, say the ones are inside the plane, zeros outside. Okay. So the family of planes shatters that. And it turns out if you, okay, it works for 3, then it works for 4, it works for 5, at some point it quits. And after that point, it turns out that the number of I can get through my classifier interacting with my points, instead of scaling like 2 to the n, it scales like n to the VC dimension. And that's the big point here, is at the bottom that I guess I can, let me change this so I can go like this, put it up there, is that the naive approach for bounds says, well, the probability of having this error bigger than epsilon is this number of things in my classifier set times e to the minus c times n. Well, if that number of things is infinite, I'm hosed. That doesn't work very well, right? But it turns out that Batnick and Trebenicus figured out that actually, even if you have an infinite number of things in your classifier, all you really care about is the VC dimension. So you end up with this other thing that says it's like this. It's polynomial in n times an exponential in n thing. And so that was their breakthrough. That's why they're famous. Is because as long as you have finite VC dimension, you can learn it. You can learn the classifier from the data. And that's the whole point, is this shattering is an integral part of learning. And that's what I have here. The art of learning from data is in some sense the art of finding these classification, the set of classification functions or sets that shatter big enough sets, but not too big, right? If your set of classifiers can shatter any set, it's useless because you can match any input data, and your generalization error, that is new data, will be random, whether you're classifying correctly. So it's this art of finding something that's, or you can, another thing it's done is you can find sequences of classifiers that you use carefully and you tune where you use it. Okay, well, that is the end of that, except for the advertisements. So we have these iSciMath coffee discussion things Mondays. And depending upon if you want to come there and help make coffee or whatever, it starts at 11. I think officially the announcement is 12, but anyway, 11 to 2. Fridays is 1 to 4. Dr. Michael or I. And hopefully, as we give these talks, there's going to be a lengthening stream of people we say to talk to you here, because we need more people involved, more students. Our ambitions are to, every class we teach to end up generating a book. We have 2 books in progress. One that's almost done from some of those classes you saw. And anyway, that's that. I have minutes for questions.
Here you're looking at this sort of siloed nature, physics and math. Are there other models or potential places to just push these ideas? I mean, for example, the bioscience is really siloed way to describe it. And are there people who are thinking the way you do, or they talk to you?
Well,
not necessarily relating now.
Yeah, okay. So people we've gotten some traction with are obviously physics. And in math, there's biology, mathematics, there's students in mathematics. A lot of people in physics, that's why I'm here. And then economics and engineering, we have some traction. So
Between the two?
no, between like getting them sucked into this whole vortex for trading. So that's where we've gain traction. Now, tons of people should be involved. Like the CDLG thing, we had artists, we had Reza, you know, in art, we had sociologists involved, we had other people involved, and then the shutdown happened and that kind of dissipated all of that. But yeah, I think I would love to have, if I were a billionaire, I'd build a building, move physics in and move the people from math and move the people, anybody who had this agreement to this. One thing is getting people moved out of their silo. They come here and they, you know, you're assistant professor, you don't have tenure, so you gotta do these things. And then by the time you get tenure, you're like, yeah, they take all their darts away because you do that like that. I mean, it's ridiculous. And I don't know how to get people out of those modes. There's a few people that get out of them. Unfortunately, this place has a problem in that it doesn't help people who are more ambitious to do different things, and very often they leave and go somewhere else. That's a big problem. I know that I have two people in engineering that I wanted to work with. Soon after I started working with them, they're off somewhere else, right? But how do you find people who, even if you just wait till they're done with their getting tenure, how do you find people who are just willing to move outside? Like I know I'm on YouTube. I don't care. Like I put things in archive, and if it gets published, beyond that, I don't care at all. I want to do this thing I see, and I want to get people using mathematics in a certain way. I don't want to get students doing things in a certain way. But I know that's unreasonable for me to expect other people necessarily to be like that, but I like to pull them a little bit that way. So they move them, once they have whatever it is that's stable, to be able to do stuff. And that's the challenge. And I think partly it's going to be, as they see a few of us doing things that are cool, you'll be able to slowly, that's the theory of it. I know for sure if I had $1 billion and could build something and be more visible, you could get more people involved, right? But you don't have that, won't do that. But I mean, you know, Los Alamos was a good game.
To utter the famous lines is more of a comment than a question.
Yeah.
I just wanted to thank you for the candidness of your talk, because I think it's really important that people see others they can look up to that didn't always have it figured out or didn't take a traditional path. I think that's really important. And I really appreciate personally your vulnerability aspects that you were talking about. So thank you.
Yeah, I don't know how to operate other than that now.
And
Yeah, that was right, you know, because my life literally depends on it. Yeah, and my brother's life, literally, he'd be dead now for sure. I mean, class 5 kayaking usually kills people eventually. As an example, he's the guy that did that. I climbed without ropes. Drove my car as fast as it would go. Luckily, I didn't have terribly fast cars. He was 120. If I had a car that go 200, I might not be alive. But
Previous slides.
the previous slide, this one.
Yeah, so you mentioned that's a big set, enough size. How big is this?
Well, so you look at that. So let's look back at this thing right here. Okay. So this probability of your estimated thing being but more than epsilon worse than the best estimator in your class. The bound is n to the VC and e to the minus Cn, okay? When you look at that, you ask, well, how many data points do I have? And if you have like 1 million data points, then, and you want that to be small, then VC dimension has to be something, right?
You need to worry about this overfitting versus this underfitting.
That's what this is about.
And you're saying that's good enough, just using that.
Well, this actually tells you that, say, for the VC dimension is low enough, it says that if it's only 3, it says that once I get to 3 data points, if I got like 50 data points, then I can't fit an arbitrary classification on 50 data points. Right, instead of having 2 to the 50, have 50 to the 4. Right, so anyway, it's you just play with these numbers when you figure out how big your classifier. And then, you know, as you have more data, you can always have a sequence of classification families that where the VC dimension diverges, but you just tune where you sit for the particular problem you have.
Actually, I don't know where these are derived, but looking at your drawing there, are you basically saying the size or the point that's close to your decision boundary is really the carrying the most?
Well, that's the idea from support vector machines,
Yeah.
the supporting guys. No, I'm not talking about supporting guys here.
Oh,
I'm just talking about if I put a 0, 1, I assign 0, 1 to Z1 to Z2 and Z3. So I have 8 different assignments. Can I get a plane? Can I get a plane that generates, if I say inside the plane, in the green, that's going to be 1s, and outside it's 0s. Can I find a plane that will make that assignment no matter what assignment I have? The answer is yes.
oh,
If I have 4 points, it's not the case. Like, so the VC dimension here is 3 or 4. I forget which way it goes. Yeah. Yeah, for that class of, yeah.
This is all deterministically done, right? What I'm getting at is, I guess people have maybe generalized this to include noise, where you make probabilistic decision surfaces in classifying different categories of objects.
Say that again.
Is it? I'm assuming there is like no noise here or no scope for.
No, I mean, you mean that you don't, by noise, you mean you don't know what the actual class, you don't know what the labels are?
There is some random element here, right? That
Well, there's random elements here. That is,
what is that?
well, the random element is you're drawing the Z1, Z2, Z3 from some distribution you don't know. Now I have points, and then at each point there is a truth that's 1 or 0, but when I collect the data, I'm collecting that randomly according to some distribution I don't know. Typically, this is non-parametric, you don't know. So the randomness is in, so the randomness here is the sample set. Do another set of samples, another set of samples, and so the probabilities here are over the, if you have n points instead of the product of n of these guys, the probability over that. So that's where the randomness comes.
All right, we'll have to continue technical discussions down here, so let's thank Kevin.